In this video, I'm going to introduce you to two more models for hyperbolic geometry. The hyperboloid model is very similar to what we were doing with spherical geometry, except that instead of using a sphere and great circles on the sphere, we will use a hyperboloid of revolution and hyperbolas on that hyperboloid. The Klein model is closely related to the hyperboloid model. You can switch back and forth between the hyperboloid model and the Klein model very easily, but the Klein model has the advantage that it's purely two-dimensional. So let's get started. In spherical geometry, our three-dimensional model was a sphere, which I trust you all found very easy to visualize. And the points of the geometry were three-component unit vectors on that sphere, which you could identify, for example, with points on the surface of the Earth. We can do something similar in hyperbolic geometry, except that instead of using the unit sphere, whose equation is z squared plus x squared plus y squared equals 1, we're going to use a hyperboloid of revolution, which satisfies the equation z squared minus x squared minus y squared equals 1. There are solutions to this equation with both positive z and negative z. We're only going to use the positive z solutions, so the z coordinate has to be greater than or equal to 1. Obviously, the points on our unit sphere were unit vectors, and it would be nice if the points on the hyperboloid were also unit vectors. How are we going to do that? Easy. We change the formula for length so that it's the square root of z squared minus x squared minus y squared. Since this quantity is equal to 1 for every point on the hyperboloid, every vector from the origin to a point on a hyperboloid is a unit vector. Well, we want the length formula still to have the property that the squared length of a vector is its dot product with itself, and we can achieve that very simply by making exactly the same sign change in the dot product formula for two vectors that we made in the length formula. And now we have a way of defining distance. Recall that in spherical geometry, the dot product of two unit vectors was equal to the cosine of the angle between them. In hyperbolic geometry, you guessed it, the dot product of two unit vectors is going to be equal to the hyperbolic cosine of the dot product. Sorry, I said that wrong. Going to be equal to the hyperbolic cosine of the distance between them, so that the hyperbolic distance can be expressed as the inverse hyperbolic cosine of the dot product. You can only take the inverse hyperbolic cosine of something if it's greater than or equal to 1, but with our sign changes for two vectors on the hyperboloid, the dot product is guaranteed to be greater than or equal to 1. In spherical geometry, you will recall that I could characterize a line as spherical geometry, a great circle on the unit sphere, by its so-called pole, a vector of length 1 perpendicular to the plane in which the great circle lies. We can do the same thing formally in hyperbolic geometry by saying a pole is again going to be a three-component vector whose dot product with a vector on the hyperboloid is equal to 0, so that c times z minus, because we've changed the dot product, a times x minus b times y equals 0. It will turn out that such a pole has to have a negative squared length according to our new length formula. In other words, when we calculate c squared minus a squared minus b squared, we get something that is less than 0, and it's usually convenient to rescale a pole vector so that the value of c is equal to 1. In that case, of course, a squared plus b squared has to be greater than 1, and the second and third components for a pole vector can be identified with points outside the unit circle. That will turn out to be convenient when we get to the Klein model in a few minutes. So the squared length of a pole vector is negative. It turns out that in Minkowskian geometry, which is the geometry of Einstein's special theory of relativity, there are also vectors whose squared length is negative and vectors whose squared length is positive. And for reasons that will become apparent when we study Minkowskian geometry, those were called space-like and time-like, respectively. Mathematicians have extended this terminology to all geometries that include hyperbolic functions. So in hyperbolic geometry also, vectors with negative squared length will be called space-like. Those are our poles. Vectors with positive squared length are called time-like. Those actually represent points of the geometry. Now, you will recall that we were able to parameterize a circle, and therefore a great circle on the sphere, a line of spherical geometry, by means of a position vector and a direction vector. Position vector p times the cosine of some distance plus direction vector v times the sine of some distance. And we can do exactly the same thing in hyperbolic geometry. You give me a point on the unit hyperboloid, a vector tangent to the unit hyperboloid, and if I take the hyperbolic cosine of a hyperbolic distance times the position vector, plus the hyperbolic sine of that distance times the direction vector, I will get another point on the same hyperbola, and I will map out an entire line of hyperbolic geometry. Simple change. Just switch ordinary trig functions for hyperbolic functions. I can solve this equation for v to get a formula for the direction vector at point P heading off in the direction of point Q, and it looks just like the corresponding formula for spherical geometry, except we're using hyperbolic functions of hyperbolic distances. And if I now substitute various values of d into this equation, I can generate an entire line of hyperbolic geometry just as I generated lines of spherical geometry. If I want to go further in making hyperbolic geometry look like spherical geometry, I will introduce the hyperbolic equivalent of latitude and longitude. Longitude works the same way. A line of longitude runs in a circle around the hyperboloid. But instead of ordinary latitude, which runs from 0 to pi over 2 radians, I need a hyperbolic latitude that can go from 0 to infinity. It's 0 at the point on the hyperboloid where z is 1 and both x and y is 0. That's sort of the hyperbolic equivalent of the North Pole. And as c, this hyperbolic latitude, gets larger and larger, I go farther and farther and farther away from the pole, hyperbolic distance increasing without limit. Now let me turn this into a two-dimensional model invented by Felix Klein. Same Klein as in the Cayley-Klein 9-plane geometries. A point on the hyperboloid has a value of z that is greater than 1, and it also has an x component and a y component. Since the z component is greater than 1, a line going from the origin to a point on the hyperboloid will intersect the plane z equals 1, and we can find the point of intersection by saying z equals 1, and the other two coordinates are just x over z and y over z. So if we know the values of x over z and y over z, that's equivalent to knowing a point on the hyperboloid, a point of hyperbolic geometry. And when I plot this, since z is always greater than either x or y, it plots up at a point inside the unit circle. Remember, poles corresponded to points that lay outside the unit circle. If I want to make a line of hyperbolic geometry, just as I can make a line of spherical geometry by intersecting a plane through the center of the Earth with the Earth's surface, so I can intersect a plane through the origin with a hyperboloid to get a line of hyperbolic geometry, which is specified by a formula that looks like this, and that says that a times x over z plus b times y over z equals 1. When I plot that up, it corresponds to a line segment inside the unit circle. So now we've got the Klein model. The points are just points inside the unit disk. The lines are line segments inside the unit disk, and each line has a pole conveniently represented by a point outside the unit disk. And if you give me a point or line of hyperbolic geometry, all I do is extend out until the line from the origin hits the hyperboloid, and I have reconstructed the corresponding point or line of hyperbolic geometry. Now in spherical geometry, you'll recall, there's a simple test for two lines to be perpendicular. Each line has to include the pole of the other. Example, suppose that one line is the equator of the Earth and the other line is some meridian of the Earth. The pole corresponding to the equator goes through the North Pole, which lies on every meridian, and the perpendicular line to any meridian is a vector in the equatorial plane. The same rule works in the Klein model. And conveniently, in the Klein model, we can depict both the pole and the line in the same plane. And here's the rule. If you start with one line, the perpendicular line has to include the pole. Well, strictly speaking, it doesn't include the pole because the line is only the segment inside the circle, but if I extend it outside the circle, it has to pass through the pole. So now I have a very convenient technique for identifying perpendicular lines. Two lines are perpendicular in the Klein model if and only if one of them, when extended, passes through the pole of the other, and if I want to construct all the lines that are perpendicular to this line, I just consider all the lines that pass through the pole of that line while intersecting it somewhere. Now let's address the issue of length and angle in the Klein model. Remember, the points of the Klein model are points inside the unit circle. So the unit circle itself is infinitely far away from all points on a line in the Klein model, and that line, therefore, appearances notwithstanding, has infinite length. When we need to calculate distances in the Klein model, what we do is trade in the points in the Klein model for points on the hyperboloid by simply rescaling the three-component vector so that it is a unit vector. And then once we've got unit vectors, it's easy to calculate distances. In general, although the lines of hyperbolic geometry are represented by straight line segments in the Klein model, the angle between those two line segments is not equal to the true hyperbolic angle. This is a difference between this model and the Hermes-Messenger model. The Hermes-Messenger model was what was called conformal. The angle at which two lines, really semicircles, crossed was equal to the true hyperbolic angle between the two lines. In the Klein model, the angle that you see between two line segments is equal to the hyperbolic angle only in cases where one or both of the lines is a diameter of the circle. However, the really important angle is a right angle, and we do have, as I showed you, a convenient way of identifying perpendicular lines in this model. So now we can check Euclid's postulates. First postulate, 2 points determine a line. Sure enough, you give me 2 points in the unit circle, I can construct the line segment that joins them, and I can do it with an ordinary straight edge. Second postulate, given a line segment from P to Q, I can extend it as far as I like in either direction. Yes, indeed, I can extend it until it almost hits the two ends on the unit circle, and since the places where the line would intersect the unit circle are infinitely far away, I can extend it to any hyperbolic distance that I like. Third, given a center and a radius, I can draw a circle. Easily done. I just pick a center, some point inside the unit circle, and in a variety of directions, draw line segments with hyperbolic length r. Those will extend out to points on the circumference of the circle, precisely conforming to Euclid's definition of a circle. Fourth, all right angles are equal. Well, right angles are certainly easy to identify. I think in order to show that they were equal, strictly speaking, what I should do is to show you a transformation that will map one right angle on top of any other right angle. But doing that, though possible, would be, in my opinion, beyond the scope of this course. Recall that in the Hermes model for hyperbolic geometry, the circles were Euclidean circles, but the Euclidean center of the circle did not coincide with the hyperbolic center of the circle. Here's a diagram. I'll show you how to draw this diagram in R that represents a circle of hyperbolic geometry. It looks like and is indeed a Euclidean ellipse, but the Euclidean center of the ellipse does not coincide with the hyperbolic center of the ellipse. Here are 4 radii of the circle. And by Euclid's definition of a circle, each of these blue line segments has equal length, that is, equal hyperbolic length, though the Euclidean lengths are not, as you can see, all equal. And the Euclidean center of the ellipse is somewhat to the left of the hyperbolic center. Well, 4 postulates down, 1 to go, and the 5th one, as you already know from the Hermes model, fails in hyperbolic geometry. Here's a diagram that illustrates parallel lines in hyperbolic geometry. Here we have a line L on which 2 other lines L1 and L2 fall. Since this line is a diameter, the angles at A and B have the nice property that the Euclidean measure of the angle is equal to the hyperbolic measure of the angle. So this really is a right angle. This angle really is less than a right angle. And therefore, the sum of A and B is less than 2 right angles. Euclid says these lines are supposed to meet, but they don't actually meet because the place where the Euclidean lines intersect is on the circle. That's infinitely far away from any other point. So they just barely fail to meet, and in hyperbolic geometry, as you now know from the Hermes model, such lines are called parallel to one another. And the angle B you will recognize as Lobachevsky's angle of parallelism. If I make the angle B larger, I can keep it less than a right angle. So the sum of A and B is still less than 2 right angles, and line L1 and line L2 totally fail to meet. So Euclid's 5th postulate does not hold in general. And lines like L1 and L2 as in the Hermes model, are referred to as ultraparallel rather than parallel. So again, we see the first four postulates are valid. Propositions 1 through 26 of Book 1 are all valid in this model of hyperbolic geometry also. And the only thing that fails is the fifth postulate.